So welcome to this recap of tutorial 19 on integration, alternatively known as anti-differentiation. And why is that the case? The idea is that if you have some quantity, you can measure its rate of change by considering its derivative. And you go backwards. Perhaps you might need to know the initial condition, but you can go backwards by integrating. So let's do an example. Suppose you have a particle P. So you have some fixed point, and the particle starts off at P0, 8 meters away. And the particle has velocity, call this an example. So, and the particle P has a velocity v of t is equal to 4 plus 6t plus t squared. And from the picture, what we've said is that at the position at time 0 is equal to 8. So then overall, its trajectory is, well, it's how far it goes dependent on time. So it's where it starts, P0, plus the integral, so the sum of the changes of its position, which is its velocity. Use some dummy variable as s runs from time 0 up to time t. So this piece, the integral piece, becomes 4s plus 6s squared over 2 plus s cubed by 3. Remember, s is just some dummy variable as s goes from 0 to t. And so this is equal to 8 plus 4t plus 3t squared plus t cubed by 3 and minus 0, I suppose. The other end is 0. So the alternative view is that integration, alternatively, is that integration is area under the graph. So for instance, if I give you some bound, here's the constant case, say from 0 to 1, here's some constant function, f of t, let's say, is equal to some constant. Then the integral between 0 and 1 is just 1 times that constant. But we need to know, if I only gave you, if I only didn't give you the starting bound, you might be used to indefinite integrals. Which is often written something like you take some function and you write dx and you don't give any bounds. And the reason it's indefinite, and you often know that this is, well, some function f plus some constant, the integral plus some constant, is because you don't know where to start from. Perhaps perhaps you can think of the end as the final value of x, but you don't have a start. So so there are two types of integrals. So the above one, indefinite, and the alternative is definite. And in the definite case, the reason we think of it as area under the graph is, suppose you have, say, a curve. The integration is the approximation of the, say this is between A and B, is this approximation of area as these bars get thinner and thinner. So the same one. So it's the limit as this width gets smaller. So let's finish with some basic properties. So integration is linear. That is, the integration of a sum of two functions is the sum of the integrals. And the integral of a scalar times a function is the scalar times that function. And the integration is also additive on pieces. What do I mean by that? If I integrate between A to C, but the domain is split up into A, B, C, then the total integral, total shaded area, is the sum of the first piece plus the second. That is, the integral from A to C of f is equal to the red one plus the blue one. And the key ones, the key examples we need to know, which I know you have learned in other modules, is the derivative of a polynomial, which implies that the integral goes the other way, say up to some constant. Or you can write these things in terms of definite integrals if you prefer. And similarly for the derivative of the other trigonometric functions.